Welcome to The Explainer. Today, we're going to talk about mathematics, but not the kind you might remember from school. We're going to look at it as a universal language, a kind of poetry that, believe it or not, describes the very fabric of reality itself. Let's dive in. And look, this isn't just some fluffy, romantic idea. You'll hear this from scientists and mathematicians all the time. They love certain formulas not just for what they can do, but for their shape, their elegance, for the simple, beautiful truths they hold inside them. Okay, so what does a beautiful poem written in the language of math actually look like? Well, here's one of the most famous poems ever written. This is Einstein's equation for general relativity. I mean, think about it. Back in 1915, this one little line completely turned our understanding of gravity on its head. It wasn't a force pulling things down, it was a curve in the fabric of space and time. Wild. So what makes it so elegant? Well, as astrophysicist Mario Livio says, it's all in the structure. One side of that equation basically describes all the stuff in our universe, all the energy, all the matter. And the other side? That describes the actual shape of space-time itself. It's this beautiful, perfect link showing how one creates the other. But, mathematical beauty isn't only hiding in these massive cosmic equations. Let's go back to geometry class for a second. The Pythagorean theorem. It's so simple, right? But it's this perfect relationship that is true for every single right-angle triangle that has ever existed or ever will exist. That's kind of beautiful. And that's the magic of it. For mathematician Diana Taimina, it's that shock of surprise, that aha moment, when you realize that this abstract rule, a squared plus b squared equals c squared, perfectly lines up with a real shape you can draw. It's just perfect logic. So, if those equations are the poems, how do we actually write them? Well, like any language, it all starts with an alphabet, and of course, a set of grammatical rules. And you can see right here how this language gets built up. On the left, you've got the basic alphabet of math, symbols for things like equals or angle, simple stuff. But on the right, you have a whole sentence, Green's theorem. Now, you don't need to know the details, but it's this incredibly powerful idea that connects what's happening inside an area to what's happening on its edge. A whole profound statement all built from that simple little alphabet. And this right here, this is one of the absolute golden rules of that grammar. The fundamental theorem of arithmetic basically says that prime numbers are the Lego bricks for all other numbers, and every number has its own unique building recipe. It's this unbreakable rule that gives math all its power. Now, when you start thinking about this language, with its elegant poems and its strict grammar, it leads you down a rabbit hole to a really deep philosophical question that people have been debating for centuries. So which is it? Are we inventing math? Creating it out of thin air from our own minds, kind of like a piece of music? Or is it something that's already out there, woven into the universe, a fundamental law that we're just discovering? And this debate really splits the whole field. You've got some mathematicians who see what they do as a creative art, driven by beauty and elegance. And then you have others who see it as a science, a tool for finding objective truths about how the universe works, right alongside physics and engineering. Einstein himself put his finger on this paradox perfectly. See, pure math is this world of absolute perfect certainty. But the second you try to use it to describe our messy real world, that certainty becomes, well, just an approximation. It's this weird, powerful tension that makes math so incredibly good at describing everything around us. For pretty much all of human history, we were the only ones who could read and write this language. But that's just not true anymore. We've built tools, scribes, if you will, that are, in a lot of ways, way more fluent than we could ever be. Just take a look at the evolution of a tool like Mathematica. When it first came out in 1988, it was a total game changer for technical computing. And ever since, it's just kept evolving, becoming a more and more powerful speaker of this mathematical language, now all hooked into the cloud. So what is it, really? Well, you can think of it as a system designed to put mathematical discovery on autopilot. It takes that alphabet and that grammar we were talking about and just runs with it at a speed and complexity that's pretty much impossible for the human brain. And these modern tools are absolute powerhouses. We're talking about unbelievable algorithm power, industrial strength capabilities, all connected to real-time data from the real world. They can tackle problems at a scale that we couldn't even dream of trying to solve by hand. Okay, so if we have these new computational scribes that have completely mastered the language of math, where does that leave us? The original speakers. See, the language of math often shows us things that completely break our brains. Get this. In higher dimensions, which we can't even picture, it's been proven that you can pack circles inside a box and their radiuses will grow towards infinity. I mean, it makes zero sense in our world, but the math is certain. It's true. And that really leaves us with a final, fascinating question to chew on. As these powerful tools get smarter and explore these mathematical worlds way beyond our own intuition, will their biggest contribution just be finding new answers to our old questions? Or will they change the very questions we even know how to ask in the first place?